Welcome back. We will have our next speaker, Jan, from Prague, telling us something about dense inhomogeneous random graphs. Okay, it's all yours.
Okay, thank you, and thanks everyone for joining in, and thank to the organizers for organizing this nice virtual event. I will be talking about two fairly basic results concerning inhomogeneous random graphs. One of them is an older one I have with Ondráš Mathe and Martin Dolezal, and one of them is a more recent one I have with Gopal Viswanathan. Okay. I will just recall the Erdős-Renyi random graph. I will be working with the binomial model. So you have two parameters. One is the number of vertices. So the vertex set is fixed. It's integers 1 up to n. And then there is a real number between 0 and 1, p. And that's the probability with which you include every single edge. And I think all the time when I say something that you do something at random, you do that at random independently of all the other choices. Okay, and I guess so there are of course many interesting parameters or properties asymptotic properties you can study regarding this model. But maybe the main message I remember from my early classes in random graphs is that the interesting case is when p goes to 0 as n tends to infinity. So when you, on the other hand, when you fix p as a constant, say p equals 0.5 or p equals 0.1, then most questions like Hamiltonicity are quite boring. Okay. So to say this equivalently, my impression always was that when G and P is in the regime that it has typically quadratically many edges, it is boring, right? So this is equivalent, having quadratically many edges or P being set to constant. Okay. So I will show that in a modification of this model, you have some interesting things going on even in the dense case. Okay, and now let me recall what are probably the two most basic results and the two most easy results concerning G and P. So one of them concerns connectivity, the other concerns the clique number. So the connectivity one, which is really as old as the theory of random graphs itself, is that it says that if your p scales as log n over n, and the leading constant is slightly bigger than 1, then G and P is asymptotically almost surely connected. And if the leading constant is slightly smaller than 1, then G and P is asymptotically almost surely disconnected. And furthermore, in the disconnected case, there is a reason, there is a very easy to spot reason for this disconnectedness, namely, you have an isolated vertex in the graph. And of course, isolated vertex implies disconnectedness. Okay. So that's, I think everyone knows that result. And let me also read an old result of Grimet and McDiarmid and Matula. And I'm specializing that result to the case when p is a fixed constant. So it concerns the clique number, so the number of vertices of the largest clique. And the result says that that number is typically logarithmic, and the constant in front of the logarithm is 2 times or 2 divided by log 1 over p. Okay, and both of these things have very easy, like five line proofs. Okay. So let me also note that that this latter result is known even to people who have no interest in random graphs, because that's a result you use to obtain what is more or less the best lower bound for diagonal Ramsey numbers. Okay, So now I will recall this generalization of Erdős-Renyi random graphs, which emerged with the theory of dense graph limits introduced by Lovas, Szegedi, Borgs, Chayes, Sors, Westergombi. Okay, so this is a random graph model, which is also parametrized by two things. So, and the first parameter is also the number of vertices. So the vertex set is against fixed. It's just integers 1 to n. But the second parameter is much more complicated. It's not a number. P was a number. So now the second parameter is a graphon, and graphon is just a measurable function defined on the unit square, taking values in the unit interval, which is symmetric, meaning wxy equals wyx. Okay. So now, given a graphon and an integer n, how do you generate? How is this model G and W defined? Well, it has now the procedure has two stages. In the first stage, you generate what's sometimes called types. So you just throw in elements x1 up to xn uniformly at random into the unit square. Sorry, so this is important, into the unit interval. And next, for each pair I and j, of course, the question is whether I should make I and ij an edge or not. So you insert that edge with probability that you read in the graphon at position xi, xj. Okay, and on the bottom of you see an example when n equals 4. There are 4 numbers sampled uniformly on the okay. So by the way, there is a graphical representation I will be using throughout of a particular graphon, where obviously I have the unit square with the convention you normally don't use for the Euclidean plane. So normally for the Euclidean plane, the zero corner is the bottom left. Here it's top left, and the 1 corner is bottom right. So this corresponds to how you normally think or depict matrices. So you can see the main diagonal depicted there. So I generated 4 random numbers, right? And for example, the question whether I should insert a 2, 3 as an edge or not, that's something you can read at this position, right? There is a particular number depicted by the particular shade of gray, and that's the probability you should insert that edge. And by the way, the fact that the graphon is symmetric is telling you that the edge 2, 3 gets inserted with the same probability as the edge 3, 2, which better be the case in the undirected setting. Okay, and this particular example is something which actually existed in the community even before the theory of dense graph limits. This is called the stochastic block model. So stochastic block model is a particularly simple class of graphons where you have a finite partition of the unit interval. So here it's a partition into 3 blocks that induces a partition of a grid partition of the whole square. So I have 9 cells in this example, and on each of the cells, the graphon is a constant. But of course, measure theory tells us that our graphons can be much more general than that. Okay, and recall that the random graph model, each W gives you a particular model of random graphs, and these random graphs typically have quadratic number of edges, right? So asymptotically, almost surely the number of edges of G and W is quadratic in N, and the leading constant is 1/2 of the L1 norm. Okay, so with the intuition from before, one might say, well, probably this leads to, somehow all questions regarding connectivity, Hamiltonicity, and so on, they will be boring. So I will try to convince you that this is definitely not the case. Okay, so let's turn to the question of connectivity of G and W. So you give me a W, and I would like to know whether the corresponding model is asymptotically almost surely connected or not, or disconnected. Okay, and here I'm just recalling the theorem we had from the beginning, and that's about the homogeneous case. And that theorem actually seems to suggest that somehow, we are not even in the interesting setting here, because for the homogeneous case, the correct scaling, the only reasonable scaling where the question made sense or was non-trivial, was log n over n. Okay, so maybe G and W is always connected when W is not constant 0 or something like that. So let's actually investigate that. Okay. So I claim that there is one very obvious obstacle for G and W being asymptotic from G and W being asymptotically almost surely connected, and that is disconnectedness of W itself. Okay, so this is a notion. So there is a notion of connectedness or disconnectedness in graphons. Namely, I say that a graphon is disconnected if I can partition the interval 0, 1 into two sets of positive measure, like, connected components of graphs are also the sets which are non-empty. So, two sets of positive measure called R and B here, like red and blue. So that W is 0 almost everywhere on this cross section R cross B. Okay, so this is an example of a disconnected graphon, and in particular, on these two diagonal squares, one of them is light gray, the other is almost black. What happens there is not important at all. Could be constant, could be some crazy measurable function. What is important on R cross B, the graphon is 0. Okay, so that's what and now I claim that if W is disconnected, then G and W is disconnected asymptotically almost surely. Why is that? Because if you consider this two-step procedure of generating G and W, first throwing in these elements x1 up to xn at random, what will happen is that a positive proportion of these vertices will end up with the red type, and positive proportion of these vertices will end up with the blue type. And now you pass to the second step when you are supposed to generate these edges, and you see that each red-blue edge is inserted with probability 0. So really, okay, and the law of large numbers tells you that actually there will be asymptotically almost surely at least one red vertex and at least one blue vertex. So, you really have a non-trivial, you get at least two non-trivial components in this G and W. Okay. So there is a question in the chat, if anyone could graphon describe. Well, yes, graphons could somehow, a modification of that graphon could describe somehow sparse random graphs, but I will not get into this. Maybe at the end. Okay. Okay. So now, is that it? So is it that if the graph is not if the graphon is not disconnected, I always get a connected, asymptotically almost surely a connected random graph? And the answer is no, not necessarily. So let's consider this graphon, which is defined as wxy equals x to the 6, y to the 6. So exponents are somewhat arbitrary, but this is definitely a definition of graphon because x is a number in the interval 0, 1, so I can take its 6th power. Y is a number in the interval 0, 1, I can take its 6th power. Obviously, what I'm getting is something which is symmetric in x and y, and it's a number between 0 and 1. So it's a graphon, and you can easily check that it's connected because there are actually no zero sections at all. Okay. Well, let's think how the generation, how G and W looks in this case, right? So let's again look at the first step of generating G and W, which is you just throw in n many points into the unit interval. Okay. So in particular, the spacing between these points is roughly, so between, as you go from left to right, the spacing between the points is roughly or is roughly 1 over n. Okay, so roughly the leftmost point of all these points you threw in is of order 1 over n. Okay, let's say that the leftmost point is at most 1 over square root n. That's definitely generous enough. Okay, but that means that the leftmost point, the value with so from the point of view of this leftmost point, let's call it xi, with respect to any other y, the value wxi comma y is at most 1 over square root n to the 6 times, well, at most 1 to the 6. So that's at most n to the 1 over n cubed. Okay, so the leftmost point is in a situation where it could have any number of friends between 0 and n minus 1, right? That's the most friends you can have in a graph. But each of those people want to become his friend only with probability n 1 over n cubed. So, I'm sorry, you're going to have no friends. Right? So in this example, what I showed is that actually asymptotically, almost surely, you will have at least one isolated point. So what if you think about this argument or this example a bit more generally, what it shows is that you need to introduce this notion of degrees, which is of a graphon, right? So for a given x, I just look at the slice, at the corresponding slice of the graphon, and I integrate, and I call it the degree of x. Okay, and somehow in this example, the tail of vertices of very low degree, of dangerously low degree, those that would be likely to become isolated, was too heavy. That was the reason for the existence of these isolated vertices. Right? And somehow, how heavy this tail was obviously had to do with the power, right? So the bigger power I have, this power 6, the bigger I have it, the heavier the tail. Okay? And that's indeed our theorem, right? So you give me a graphon. The question is the graphon, is the corresponding random graph asymptotically almost surely connected or asymptotically almost surely disconnected? So first you look at the graphon itself. If the graphon is disconnected, then indeed, there was this macroscopic reason for disconnectedness. So G and W will be asymptotically almost surely connected. And if W as a graphon is connected, then what you do, you introduce for every alpha, you introduce this number as alpha, which just measures how many elements of your ground space there are whose degree is at most alpha. Okay, and the theorem says that if S alpha is much less than alpha, as alpha goes to 0, then G and W is asymptotically almost surely connected. If S alpha is much bigger than alpha, as alpha goes to 0, then G and W asymptotically almost surely has an isolated vertex and hence is disconnected. Okay, and then there is this third case where, you know, I didn't write the full statement. There should be some lim sups and lim infs to cover all the other cases, but I think everyone would be able to write it down, and basically then the probability is strictly between 0 and 1. Okay. So that was the case of connectivity, the characterization of W's, which give you asymptotically almost surely connected or disconnected random graphs. Okay, so let's actually quickly turn to the clique number. So again, I'm starting with the homogeneous. I'm recalling this old result of Grimet, McDiarmid, and Matula about the homogeneous case where the clique number for P constant was logarithmic, and they found out the leading constant. Now, what does it imply for the inhomogeneous case? So suppose that W is a graphon, and it's uniformly away from 0, and it's uniformly away from 1. Okay, so, you know, I picked these two pretty much arbitrary constants here, but, you know, 0.01 and 0.99. Okay, so that means that our inhomogeneous random graph, our random graph model G and W is stochastically sandwiched between Erdős-Renyi random graph 0.01 with edge probability 0.01 and Erdős-Renyi random graph with edge probability 0.99. Okay, and to both of the extremes, I can apply the Grimet-McDiarmid-Matula result. So I have a logarithmic lower bound and a logarithmic upper bound for the clique number. Okay, so the challenge now is to find the constant, let's call it CW, so that in my model G n, W, the clique number grows as CW times log n. Okay, and so what I would quickly like to do is I would show you some heuristics how we do it. Okay, so first let me recall what's pretty much the proof, or at least half of the proof. That's the first moment calculation. You always need to accompany those with second moment calculations in the Erdős-Renyi case. In other words, in the simplest case, when W is a constant graphon. You know, the W being constant graphon, constant P corresponds to the Erdős-Renyi case. Okay, so what do you do then? It's really like page 1 of every random graph book. Well, you set up a number K, which is C times log n. Okay, and you will optimize for this constant C later. And you introduce a random variable which counts the number of cliques of size K in your random in G and P. Okay, and there is a formula for the expectation. More or less, you care whether the expectation for which C's the expectation goes to 0 or goes to infinity. Okay, and what you get is that depends on this whether. Okay, so that's the bottom of my slide, whether 1 plus log P times C half is smaller than 0, in which case you will have asymptotically almost surely no cliques, or it's bigger than 0, in which case asymptotically almost surely you will have many cliques of size C times log n. Okay? Okay, so we managed, I mean, I didn't really do anything, but I could pretend I managed to compute the clique number of G and W in the simplest case when W is a constant graphon. Okay, so let's actually try to move to the next simplest class of graphons, which are 2x2 step graphons. Okay, so here is an example on the right-hand side. You can see it. It's a 2x2 step graphon. One block has measure 0.7, the other has measure 0.3. And I have two diagonal probabilities, P11, P22, and one off diagonal probability, P12. Okay? And now I would like to know in this model, what is the size of the largest clique? And somehow, if I could repeat the same argument as before, set k equals c times log n, and count the number of cliques of size c times k, but actually what you see immediately is that somehow that's not, you need to refine that approach, and rather than tracking the number of cliques of total order c times log n, you want to track the number or count the number of cliques which have c times log n vertices in the first part, c1 times log n vertices in the first part, c2 times log n vertices in the second part, and you want to maximize c1 plus c2. Okay, so by pretty much repeating the argument, you get a calculation for the expectation, and that again leads to a certain expression. That's the bottom of the slide. Leads to a certain expression, and the question whether that expression is positive or negative. Okay. By the way, note that in the expression, the values 0.7 in the expression at the bottom, the values 0.7 and 0.3 don't appear at all. Somehow they are not important at all. The reason for that is that in the formula for the expectation, they only appear in the binomial coefficients, these constants 0.7 and 0.3. And somehow binomial coefficients in this regime are much more sensitive to what is happening in the bottom part than what is happening in the top part. Okay, so it doesn't really matter. I could have, this model with respect to the clique number behaves the same if I change 0.7 to say 0.8. Okay, so I have, this is the same slide, except I deleted what was not important from the slide, right? This is a formula for the clique number in the 2x2 step model, okay? Which is an optimization formula where your optimization goes over C1 and C2, and there is a certain condition which I would call non-negativity or positivity condition, which I would say that it has two parts. One I would call the entropy, because that part comes from binomial coefficients, and one I would call energy, because that part comes from the probability of any particular set of C1 log n plus C2 log n many vertices creating a clique. Okay, what our main theorem is that the same holds when W is a graphon. The same sort of optimization idea holds when W is a general graphon. Of course, now the difference is that you don't have two types or three types, but you have actually continuum many types. And so you don't have C1, C2, C3, C4, but you have continuum many types, and these continuum many types are, coded by measurable functions, taking values on your ground space on 0, 1, and the values are between 0 and infinity. Okay, so thank you for your attention.